In this video, we're going to talk about implicit differentiation. So we're dealing with functions of two variables that are not given with an explicit formula, but given implicitly. We'll talk about graphing them, finding their derivatives, doing tangent lines. So here's an example of an implicitly defined function, x squared plus y squared equals 25. Compare that to this explicitly defined function, y equals the square root of x squared minus 25 right here. So in this explicit definition, if I tell you x, you plug x in and you calculate and you get y exactly. In this implicit kind of equation, if I give you an x, you can figure out y's that go with it, but you kind of have to solve for y. So you're given y implicitly instead of explicitly like this formula. Now I call this an implicit function. I'm using the word rather loosely. If you graph all the solutions of this equation, you get a circle of radius 5 centered at the origin. And if you remember pre-calculus, circle does not pass the vertical line test. That is not the graph of a function. So it's sort of not quite right to call this a function. But anyway, it's two functions glued together. So each part of it is a function, and you kind of glue the pieces together. In fact, this explicit formula down here is the top half of this circle. If you stuck a minus sign right here in front of the square root in this explicit formula, you get the bottom half of the circle. And if you glue those two semicircles together, which are both functions by themselves, those two functions together give you the whole circle. So we'll call it a function. Graphing in an implicit function in Sage is fairly simple. There's a command just for that. It's implicit underscore plot right there. And it requires 3 arguments, an equation that it's going to graph. And remember, an equation in Sage needs to have a double equal sign. And then you need to specify the plot range for the first variable and the plot range for the second variable. This looks a little different from the way I normally do it with the regular plot command with the xmin, xmax, ymin, ymax. We'll see that down below. And I'm going to add a couple extra options. Axes equals true will turn on the x and y axes, and frame equals false will turn off this frame, which by default Sage does not use axes for these implicit plots. It instead puts a little frame around the outside. But I want it to look like our normal xy axes, so that's why I'm going to do that. So let's graph this circle first. Remember, you get x for free as a variable, but if we're going to use a variable y, we do need to declare it. So %var y before you use y in the implicit plot. So here it is, implicit underscore plot, parentheses. Here's the equation that defines our implicit function, x squared plus y squared equals 25. Notice again the double equal signs here. And then you put a comma, and this is how you specify the range for the x variable. You put parentheses, and then x to say, okay, I'm talking about x, comma, and then minus 5 to 5. This is the x min and the x max. You could actually do this on the regular plot command too, though I didn't teach it that way. And then you put a comma, and then parentheses y minus 5 to 5. Now this part doesn't work in the regular plot command because there's just the one variable x. You have to use the y min and y max, which is why I didn't do it back then. But anyway, this specifies that y goes from minus 5 to 5 and x goes from minus 5 to 5. Of course, they don't have to be the same. You could make this minus 10 to 20 or whatever you want. But for this assignment, probably just leave it here is okay. And here I turned on the axes, I turned off the frame, and I run that, and what I get is this circle. Here's a second example. So here's kind of a complicated equation. And if you wanted to graph this with your graphing calculator, you'd have to try to solve this for y, which is possible. This is a quadratic, it looks like, in y. Well, anyway, that would be kind of a mess. But it might be possible. But here with our implicit plot, we can just put in this equation just like it is. So here's implicit plot. We type the equation just like it is, remembering the double equal sign. I'm going to graph this from minus 2 to 2 on both axes, and there's what it looks like. It's this little loopy thing. Now we're not used to seeing this from, like in pre-calculus, because this is not the graph of a function. Now again, you can take two functions and glue them together and get this thing. But this is not the type of thing that you normally see in pre-calc things with loops like this. So some of these can be a little more interesting. Now that we know how to graph, we want to find the slope of these functions. So we need to find the derivative. We want the derivative of y with respect to x as normal. To do that, that assumes that y is a function of x. So to calculate the derivative in Sage, we need to tell it that assumption, y is a function of x. Here's how you do it. You say y equals a function, and then this is the name of y. Y is a function called y, and it's a function of x. That's what this parentheses x stands for. You can just copy and paste this into your assignment. This is the syntax. You got to get it exactly like this. It's the same every time. So this tells it that y is a function of x. Now we can take the derivative using the regular derivative command. So here's our circle. I want to find the derivative of y with respect to x. So rather than trying to solve for y and doing it like we did before, we can just take the derivative of this equation. So here's the regular derivative command. We type the equation in. Remember double equal sign. X is our variable we're taking the derivative with respect to. Here's what comes out, and then the show command gives me this nicer looking thing. Now this thing right here, this is kind of a curvy looking d thing. This is the regular d over dx. You'll learn about this symbol later on in Calculus 3, if you take that. But for this class, you can just think of this as d over dx. This is the derivative of y. So this whole thing is y prime. Notice here, this is not y times x. This is y of x, function notation. Remember we told Sage that y is a function of x, and so it writes it as a function, just like f of x. So don't think of this as y times x. This is just all y. Y of x is just y. And d over dx of y of x, all of this is just y prime. Okay, now this is an implicit formula for the derivative. We might want to try to solve for that. So here I said solve this derivative, the derivative of the circle, solve it for the derivative of y. And you can just type in derivative of y there and it will know what you're talking about. So here's the solution, and here's the nice showed one. The derivative of y is equal to negative x divided by y. That's what it tells us. So if we kind of rewrite this in the normal symbols we use, here it is, dy dx, or y prime, is negative x divided by y. All right, here's the next example, that little loop graph, remember we did earlier. So we need to tell it that y is a function of x, and then we can solve this equation. The equation we're trying to solve is the derivative of this implicit function. What we're trying to solve for is the derivative of y. Watch out for parentheses here, so we need opening parentheses for the solve command, opening parentheses for the derivative command. Here's the equation, which also involves some parentheses, comma x to take the derivative with respect to x. Then that's the end of this first derivative command. This comma is part of the solve command. Remember, the solve command takes two things, an equation to solve and a variable to solve for. This is the equation we're solving. This is the variable we're solving for. We're solving for the derivative of y. So that derivative needs its own parentheses, and this last parenthesis is the end of the solve command. All right, so here's what we get. Derivative of y is equal to this thing. So here, let me rewrite that in our normal notation, dy dx equals. Watch out for this minus sign in front. Sometimes, see there's a little space there. That minus sign kind of merges in with that division bar. So be on the lookout for that minus sign. You can see it up here in the output, the non-pretty one. But in this one, you got to make sure you notice that little space right there between the minus sign and the fraction bar. Notice that all the y of x's I replace with just y. Y of x becomes just y. All right, and this is a formula for the derivative. Notice here that these derivative of y involves not only x but also y. So we're not used to that in our regular non-implicit functions. When you have an explicit formula and you take the derivative, you get the derivative of y is equal to something involving just x. But here we have both x's and y's involved. Now that we can do derivatives, we can find tangent lines. So tangent lines need the slope at a particular point. We found the derivative function. Now we just need to plug in a particular x value and a particular y value to get the slope at a particular point, and then we can use the tangent line. So remember our tangent line formula, it's the y value, which comes from the function, plus the derivative, the slope, which comes from the derivative, and then x minus whatever particular x value you're looking at. All right, so let's go back to the circle. X squared plus y squared equals 25. 3 comma 4 is a particular point on that circle. I want the tangent line at 3 comma 4. Now up above we found the derivative of dy dx was negative x divided by y. So the slope at 3 comma 4 is negative 3 divided by 4. You plug in x equals 3 and y equals 4. So minus 3/4 is the slope, and you put that into the equation for the tangent line. It's y equals the y value is 4, plus the slope is minus 3/4, times x minus the x value is 3. Now let's go ahead and graph those two together. Now before plotting, you need to declare y to be a variable again. Remember to do the derivative. We told it that y was a function of x. That will mess up the implicit plot. You'll get an error. So we have to declare y to be a variable again. Clear that function part out. So here's the implicit plot. X squared plus y squared equals 25. Remember the double equal sign. And here's the plot range, and so on. And then we're just going to add on a regular plot. We don't need implicit plot to graph the tangent line. The tangent line has an explicit formula. So you're going to add on just a normal plot. And here's the formula for the tangent line, which is splitting across all these lines. Sorry about that. 4 minus 3/4 times x minus 3. Here's the regular x min, x max, y min, and y max. I didn't put a y min. I didn't need it, but I could have. I put the colors red. I added a point here at 3, 4, the point of tangency, this black dot, just so you can see that's where it's tangent. And if you were to zoom in on this graph by changing these plot ranges here on both the implicit plot and the plot of the tangent line, if you were to zoom in on here, you would see that this line would very closely match the circle near 3 comma 4. Let's go back to that one with a little loop. We've calculated the derivative up above. It turned out to be this. I want to plug in the particular point 1 comma minus a half and find the tangent line at that particular point. So I need to substitute in this messy derivative formula x equals 1 and y equals minus a half. And there's different ways you might do this. The sort of just naive approach would be copy and paste. So I went up above to the derivative and I just highlighted and copied. So go up here. Where did the derivative go? Here it is. This is the derivative right there. The answer. Hit Control C and copy. That's the derivative of this function. And then I just came down here and I pasted it in and I erased all the x's and put 1, and I erased all the y of x's and I put minus a half, and that's what happened. What came out is minus 9/8. Okay, so that's the slope, and I'll do another example of that later. So we have y equals the y value, minus a half, minus the slope, or well, plus the slope, which is minus 9/8, and then x minus the x value, which x is 1. And then we'll go ahead and graph it, and we'll see here this tangent line here at 1 and minus a half looks tangent. Everything seems to be working nicely. All right, example 7 here is the one that I'm going to put all the pieces together. Follow this example for your own assignment. I'm going to do the derivative and get the slope and find the tangent line and then graph the function and the tangent line, and that's what your assignment is going to look like. So here's our formula. Complicated, ugly mess. Be very difficult to put this in an explicit formula, so it's nice that we got this implicit thing going on. Here is the particular point I want. I call it AB, and it's 0.5832 is the x and 2 is the y. So first off, let's find the derivative. And to find the derivative, you need to tell it y is a function of x. You need to do this again because remember just a minute ago we said that y was a variable so that we could graph it. So now we have to go back to being a function. It's a little irritating. You got to switch back and forth. y is a function, y is a variable. Y has to be a function to do the derivative, and y needs to be a variable to do the graph. So you're going to have to kind of go back and forth. All right, solve, and then type the derivative of the equation that was given. So here's the first derivative. This is the equation of that we're trying to find the derivative of. Don't forget double equal sign. And what were we solving for is the derivative of y. Okay, so you could just copy and paste this whole chunk of code and replace this right here with whatever equation I give you in your assignment. Okay, that's the thing that changes. Everything else stays the same. And out comes this formula. And you can see the derivative of y is this big, complicated thing. Now I need to substitute these two numbers in. And rather than copying and pasting and replacing all the numbers, I'm going to call them A and B. I'm going to give them names. So let's see if I can copy this. Sometimes this thing is a little sensitive with copy and paste. I think I got it. So I did it down here already, but let me do it again. So there is the formula for the derivative. This is dy dx. All right, I'm just copying the part after the equal sign. This diff stands for derivative. It's a shortcut for derivative. Derivative of y is this mess. That's what I copied. And I want to replace the x with the number 0.5832. And I want to replace y with the number 2. And I called it A and B just to make them different so I could see which ones I had replaced here. I don't want to overwrite the variable x because I want to use variable x. So I'm going to go through and all the x's are going to become a's. So wherever I see an x, not this one. Now this one, that's not b of a. That's what I sometimes see. People say, okay, y becomes b and x becomes a. No, that's a mistake. Y of x is function notation. This is not y times x. This is not b times a. This y of x, the whole thing, becomes the number 2. All right, so x by itself becomes a, and y of x, this whole thing, y of x becomes b. That's what's going to become 2. Now, you can just type the number if you want. It'll be a little simpler if you use a and b like I did, because, well, the b doesn't bother you much because it's just 2. But with a requires you to type at least 5 things, 0.5832. And you don't have to worry about that. The other thing is if one of these were a negative number, in fact, I didn't mention that. Let's go ahead and run this. We get the same answer. Up here in this last example, notice that we had y was negative 1/2. So I needed to replace the y with negative 1/2. And there was a place right here where y is squared. And so I had to put parentheses around the minus 1/2 in order to square the whole thing. Otherwise, the minus wouldn't have gotten squared. And in fact, only the bottom, if I took away these parentheses, only the 2 would be squared. Now the 1, doesn't matter. But if this was 2/3 and you squared it, you definitely need parentheses there. So that whole parentheses thing you don't have to worry about if you use this little a and b. That'll take care of it. So if b was negative 2/3, you wouldn't have to put parentheses around the b. It's already taken care of by the fact that you've put it in this variable. So that's another advantage of this approach, as opposed to just manually typing all the numbers. So that's what I'm going to suggest you do in your assignment. Copy and paste the derivative here and replace all the x's with a's and the y of x's with b's. And let's go ahead and get rid of this. I already had it there. And then hit run, and out comes your solution. Now if this doesn't come out to give you the a decimal approximation, if there's some square root or exponential or log or something involved there, you might have to convert this to decimal using the capital N command. But since we're having decimals go in this example, then decimal came out. Okay, so I'm going to copy and paste this number for the slope. Here it is. Remember, the tangent line is the y value, which is b. I already called it b, so I don't have to type it again. I'll just put b there. Plus the slope, which I copy and paste from here, multiplied by x minus a. So you can copy and paste this chunk for your tangent line. You've already got your a and b in there. All you need to do is replace this slope with the answer you got up here. And out comes the answer for the tangent line. Now we're ready to graph. So remember to reset the y variable, %var y, implicit plot, and then type in your formula. You did it up in the derivative, so you can copy and paste it. You don't have to type the whole thing again. And the rest of it you can just leave. I've kind of already built everything in. I put TL here. We define TL, so if you redefine it for your assignment, you don't have to type anything here. It's already TL. I put the point as A and B, so if you use the A and B like I did, it's already defined. You don't have to change anything. So on your assignment, you can copy and paste this whole chunk, and all you need to do is replace this formula with the formula in your assignment. Well, in this example, here's what we get, this little kind of, I don't know, 3-leaf thing. And here's the tangent line right there. Looks like it's following the curve. That's good. Now this is a double check of your work. If my line like went this way and didn't look at all tangent, then I would know I did something wrong. So this is a good check. All right, so your assignment looks just like this example. I would suggest you follow this example, copy and paste, and then just change what you need to change. Now before we stop, I want to do a couple of 3D examples. This is not going to be in your assignment, but if you want to graph an equation that has 3 variables, you can use this implicit plot 3D command. And it has some nice features here, the way you can do with the graph. So implicit plot 3D, give it an equation of 3 variables. I declared x here, which was not necessary, but that's all right. Might as well. X, y, and z. This is the equation of a sphere. X squared plus y squared plus z squared equals 25 is the equation of a sphere of radius 5 centered at the origin. You have to specify the plot range for all 3 variables. Now we're used to doing x and y, now you just need to add z. And of course it doesn't have to be x, y, and z. It can be any 3 variables you want. This could be a, b, and c, or u, v, and w, or whatever. Just use the letters in the right spot. And so here's the graph. And if you have a mouse wheel and you have your cursor here over this graph, moving the mouse wheel zooms in and out on the thing. So you can zoom by turning your wheel. If you click and drag, it spins it. Now it's not so interesting on the sphere. Let's do something a little more interesting. So here I'm graphing the sine of x squared plus y squared minus z squared minus 36. Now when if I set this thing, the thing inside the sine, if I set that equal to 0, I would get a sphere of radius 6. But I'm putting kind of that sphere thing inside the sine function. And what you get is this kind of a sphere within a sphere within a sphere. Now the frame here, the end of my plotting, is cutting off the end of this sphere. But see inside there's kind of this sphere in there. You kind of see, and then it looks like there's another sphere and another sphere. Here you can kind of look between the shells. So kind of a strange looking thing. And again, you can zoom in, you can zoom out, and you can get closer and see what's going on. Now, one last example. This is kind of a fascinating one to me. I stole this from a Sage tutorial, which you can go find the original. I think William Stein, the Sage founder and guru, I don't know if he came up with it, but I got it from something he had done. So it's based on the golden ratio, which is built into Sage. It has this cosine of x plus the golden ratio times y, x minus ty, and all these different cosines of x's and y's combined together with this golden ratio thrown in. And don't ask me where these numbers came from. I don't know who came up with this formula, but the picture is kind of interesting. There's this sphere inside, and then this, I don't know, looks like some sort of chemical structure to me on the outside. It's this little cage thing, which I always thought this one was interesting. So you can play around with that. Again, you can zoom in, you can zoom out, and you can turn this around. If you want to change this R, that would change the plot range. I don't know what it looks like elsewhere. You can play around with that and have fun. I didn't put any of those on your assignment, but I don't know, they're more fun than your assignment, so you can don't spend too much time with those. Okay?